The salt ring is still holding for our victims as we continue to understand delta G of the system. We can now say that the sign of delta G determines spontaneity, but it was going to be the magnitude of delta G that tells us how spontaneous it is, meaning we need to be able to calculate delta G, folks. So to do this, we're going to use standard free energy change, or delta G naught of the system, meaning that we're going to be looking at free energy change under standard state conditions, okay, folks? So standard free energy change expression can now be calculated as delta G naught of the system, which is equal to delta H naught of the system minus T delta S naught of the system. And this relationship allows us for the calculation of any one of these three variables when provided with the other two. So to solve for delta G naught of the system, and of course spontaneity and the extent of spontaneity, we must find our delta H naught of the system. Now, delta H naught of the system is interchangeable with delta H naught of the reaction. Similar to delta G naught of the system, it's also interchangeable with delta G naught of the reaction. So sometimes instead of saying delta G naught of the system here, you might see it say reaction as well. All right, so delta H naught of the system is interchangeable with delta H naught of the reaction. And to solve for delta H naught of the reaction, similar to Chem 101, we're going to take the sum of the moles of the products and multiply them by their delta H naught of the formation value. We're going to subtract that by the moles of the reactants and that are going to be multiplied by their delta H naught of formation value. Then we're going to subtract by temperature, which is in Kelvin, and multiply by delta S naught of the system. Now, delta S naught of the system is equal to delta S naught of the reaction, of course, because it's interchangeable. And delta S naught of the reaction is equal to the sum of the moles of the product, which is going to be our multiplied by its S naught value, subtracted by the moles of reactants, multiplied by their S naught value. And of course, we're taking the sum of all this as well. All standard values that we see here will be given to you in calculation, so you don't have to worry about memorizing those at all. Now, let's focus on units. Delta G has overall units of kilojoules or kilojoules per mole. Then we have our enthalpy, or our delta H of the reaction is going to have units of kilojoules per mole. Our delta S of the reaction is going to have units of joules per mole Kelvin, and our temperature is going to have units of Kelvin. We have to make sure all our units are the same so that we can be able to use this expression for calculations. So that just simply means converting our delta S of the system from joules per mole to kilojoules per mole. That's all you have to do. That way we can just basically be able to get all the units we're looking for. Now you might say, wait a minute, I thought delta S naught of the system was joules per mole Kelvin. The reason why I didn't put the Kelvin here is because when you multiply your delta S naught value by temperature, the Kelvin units in the temperature and the Kelvin unit for your entropy are going to cancel. So you're simply going to be left with kilojoules per mole, allowing you to subtract these two numbers and get an overall value for delta G naught of the system or reaction. Let's use what we know as a weapon to continue to help our victims temporarily. To Dad's car we go for an example, folks. So we are back at Dad's car for weapons and examples. Remember, this is the time to create and build a strategy to approach these type of problems. So you want to complete the problem with me and then think of a way to approach the problem on your own, okay? So let's go ahead and read this question. It says, calculating delta G naught of the reaction from enthalpy and entropy values. Potassium chlorate, a common oxidizing agent in fireworks and match heads, undergo a solid state disproportionation reaction when heated. Now, a disproportionation reaction is simply a redox reaction where you have a single substance that undergoes simultaneous oxidation and reduction. And so you have the single substance here, potassium chlorate, that's going to break down into two products here and be able to continue to have a redox process. Okay, of course, when heated. Now, we're going to use delta H naught of formation and a delta S naught values to calculate delta G naught of the system, which of course we can call delta G naught of the reaction, all at 25 degrees Celsius for this particular reaction. Next, we want to bring about everything we know or have learned. So we just learned that delta G naught is equal to delta H naught minus T delta S naught. So of course, we're trying to solve for delta G naught here. So we need to start making sure that we're fleshing out and figuring out how to solve for each of these variables here. So temperature is given at 25 degrees Celsius. If we add 273, we can automatically get our temperature of 298 Kelvin. So we already have that. To solve for our delta H naught and our delta S naught of the reaction, we have to take the sums of our products multiplied by our delta H naught of formation values minus the sum of our reactants multiplied by our delta H naught of formation values for the reactants. We do the same thing for our standard entropy values for products and reactants for delta S naught of the reaction. Okay, so this is already going to be given. And so when I set up my overall reactions here on this side, you'll see that these values are already incorporated. All right, let's go ahead and solve for delta H naught of the reaction. Again, here's our reaction, here's all of our products, and here is our reactant here. So we're going to take 3 times whatever the delta H naught value of this is, 1 times the delta H naught value of this, and 4 times the delta H naught value of this. All right, folks? So when I take 3 times negative 432.75, I get negative 1298.25. I'm going to add that to 1 times negative 436.7. And when I do this multiplication here, I get negative 436.7. So I have to be able to add this negative number and this negative number. And when I do that, I get negative 1734.95. Now let's talk about the sum of my reactants. I only have one reactant, so it's going to be 4 times negative 397.7. When I multiply this together, I get negative 1590.8. So I'm going to take my negative 1734.95 and subtract it by this negative number here. What I get is negative 144.2. The units are kilojoules per mole. Now I'm going to go ahead and solve for delta S naught of the reaction. Again, it's going to be the sum of my products minus the sum of my reactants. So I'm going to have 3 times my S naught value for KClO4, which is 151.0. When I multiply this together, I get 453. I'm going to add that to 1 times my KCl S naught value, which is 82.6, and I simply get 82.6. I'm going to subtract this from 4 times my S naught value of KClO3, which is going to be 4 times 143.1, and I get 572.4. Now, of course, when I add these two numbers together, I get 535.6, and I'm going to subtract it by my number I got for my reactant, which is 572.4. I get negative 36.8, and we know for entropy, the units are joules per mole Kelvin, since we did use our standard value. Now, again, we're talking about delta G naught, and so we have to make sure our units are going to match. Since I know that my delta G naught units are going to be kilojoules, I must convert from joules per mole Kelvin to kilojoules per mole Kelvin. So I'm going to take my negative 36.8 joules per mole Kelvin. I'm going to multiply by 1 kilojoule divided by 1,000 joules. That is going to be my conversion factor. And I get a value of negative 0.0368 kilojoules per mole Kelvin for delta S naught of the reaction. So therefore, I have my temperature value, my delta H naught of the reaction, and my delta S naught of the reaction. I can plug my values in to solve for what the question wants, which is delta G naught of the reaction. All right, so plug into my values. My delta H naught is negative 144.2 kilojoules per mole. I'm going to subtract that by my temperature, which is 298 Kelvin, and multiply that value by my delta S naught of the reaction, which is negative 0.0368 kilojoules per mole Kelvin. So when I multiply these two numbers, my Kelvin is going to cancel, and I'm going to get negative 10.9664 kilojoules per mole. So I'm going to take my negative 144.2 kilojoules per mole and subtract it by my negative 10.9664 kilojoules per mole. I get a delta G naught of the reaction of negative 133.2 kilojoules, or kilojoules per mole. And when you're thinking of significant figures, because I always want to layer that little bit of information in, a lot of times the significant figures are going to be based on those standard values that you are given. So from the standard values, we were given one that are like 4 significant figures, which is why my delta G naught of the reaction is 4 significant figures here. Okay, using this new weapon of information helped to settle the ghost for now. Let's continue, folks.